Thank you so much, Bodo, for the introduction. This is Amir Shaikhha. You can call me Amir. Today I'm presenting a series of line of work on basically democratizing data science by leveraging structure, or basically the title that I chose for here to make it more array-like is actually array and data processing by leveraging structure. And this is a joint work with a bunch of collaborators that you can see here. Many of them are actually very well-established researchers. Most of them are on the left side, actually, your left side. And the right ones are mostly my students. So let's first start with the motivation. So we are living in an era where we are surrounded by a lot of data. So on this slide, you can see that in every single minute, how much data is being produced throughout the web. And so in order to, just data for the sake of data is going to be useless. We have to process it in order to extract some insights from it. We have different kinds of processing that we can do. And perhaps this workshop mostly is concerned with the data of this kind, which is basically matrices or tensors, which are very dense. However, we could have also data of this kind where many of the elements are actually zero. There is only a small portion of the data that is going to be non-zero. So for the left one, we are going to use, of course, arrays to represent them. And in this talk, I'm going to show for various types of data that are of the right form, how we are going to present them. And OK, so here I'm using a bit of nonlinear narrative. So I'm going to spoil what are we going to use in order to present it, which is basically a dictionary. So perhaps my talk would form better to a dictionary workshop. But yeah, I'm going to fit it to the array workshop. So this is the outline of my talk. So the x-axis is the time. The y-axis is the depth of the technical depth. So at the beginning, I'm going to first talk about the end-to-end data science workloads. Then I'm going to go over sparse tensor algebra. Then a bit on sparse differentiation. Then a bit deeper into structured tensor algebra. And then I'm going to say briefly sum up and tell you a bit the future line of work that we can do. So let's start with the end-to-end data science. So I said that we are surrounded by data. We need to process them. So what are we using to write programs that are processing the data? Programming languages. So which programming languages data scientists are mostly using? Python. Yes, that's the sad reality that programming language researchers invest a lot of time on developing this fancy programming language with static types and all these kind of things. And at the end of the day, people are using Python. But a bit of good news that maybe doesn't make programming language people that happy, but database people very happy, is that the second language is actually SQL. And what is the reason behind that? So if you take a look at the end-to-end data science pipeline, you can see that at the beginning, we have the data in unstructured form or semi-structured form in the form of a graph or relational data. We do some sort of data pre-processing, data wrangling. For that, we are going to use either SQL or Python libraries. We convert it to tabular data. Then we are going to prepare the data further. And in order to feed it into some statistical tools or machine learning libraries, we have to convert it into the tensor format. And then we feed it to R or Python, one of these libraries, in order to make sense of the data. So what is the issue with this pipeline? You can see that there are many different environments that are involved here. So you have to do part of it in Python, part of it in R, part of it in SQL. And if you see in the undergraduate course in databases, there have been so much theory on third normal form, how to normalize the data in order to give better structure to it, reduce redundancy. And yeah, maybe the relational data that we had at the beginning, it has so much structure inside it. But as we go through this pipeline, that structure is going to be thrown away. So we can no longer leverage that structure towards the end of the pipeline. At the end of the pipeline, it's a tensor. We have no idea where the elements in the tensor are redundant in order to perhaps do a better job, a faster job. So to classify the types of workloads that these different components are dealing with, we can basically classify them into two general types of workloads. So one is what I call the database workload, and the other one is what we call the linear algebra workload. So for example, in the database workload, we have this online analytical processing in data warehouses, where you basically do group by, aggregates, joins, and these kind of things. In the linear algebra types of workloads, we do machine learning, computer vision, or even graph processing. We can cast it as a linear algebra problem, for example, in GraphBlast, or we do scientific computation. And the issue here is that, yeah, there are these two completely disjoint communities that are not talking that well to each other. There is some effort. So for example, there is a workshop called DBPL, which is usually co-organized together with one of these either database conferences or programming language conferences, but usually there is not that much communication across these two communities. And for example, on the programming language level or on the level of the abstractions, notations that people use, in the database workload, either they're using relational algebra, or whenever they're dealing with nested data, like JSON type of data, they deal with nested relational algebra. On the linear algebra workload, they either deal with linear algebra or tensor algebra. And in terms of the frameworks, so relational database systems is the usual type of the workloads that they're using, or the poor person's version of relational algebra, relational databases, which is, for example, a framework like Panda data frame in Python. And on the linear algebra side, we have TensorFlow, PyTorch, and SciPy. So, and there is not that much communication happening across these two communities. So let's see whether there is any opportunity that we can leverage in order to marry these two communities. So let's take a very high level, very high level view of what's happening inside a relational database system. So a relational database system, you can think of it as a compiler. We have an SQL query. There is a parser, there is like analyzer, and all these kind of things that basically converts the SQL query into relational algebra. And at the end, we have an engine that takes that relational algebra expression together with the data, and it's producing the answer. And a lot of magic happens inside this engine. So what is relational algebra? As the name suggests, it's an algebra for relations. And it has a bunch of constructs. So for example, selection, projection, and join, or as well as the aggregation and group by operators. So what is the nice thing with this algebra is that it's based on mathematics and logic. And because of that, we have a lot of optimization opportunities. So here you can see a bunch of algebraic identities over these operators. So for example, whenever you have a chain of selections, we can commute them with each other. Or we can basically push selections past join. So here you can see basically that the expression that is responsible for pushing selections before the join. And in practice, what it enables is a very sophisticated form of loop invariant code motion. How about machine learning frameworks or linear algebra frameworks? We have a similar picture. We have, as input, a program that is written in terms of one of these languages like Python. And we have a library that the API we write the program using the API provided by this library. And the library behind the scenes is basically expressing all these computations in terms of linear algebra. And then there's a linear algebra framework behind the scenes that digests that linear algebra expression together with the input matrix, and it produces the answer for us. A very similar picture to the relational database system. And again, it uses linear algebra. We have a bunch of linear algebra identities that if we have if the behind the scenes, the linear algebra framework, it has implemented some of these rules, it can basically simplify the program. The first question we are going to answer is that can we have a unified framework that basically does the optimization, unifies the optimizations that we have seen? Or even better, can do some cross-optimization across these components? And of course, the answer that we are going to say is yes, we can do that. Let me give you a you have a question?
I was going to think of an application which would require them to coexist.
Yes. So basically, whenever in the end-to-end data science pipeline that you have seen, so you have the machine learning frameworks at the end, and you have your input as a relation. So you want to do some linear algebra computation, for example, over the join of these relations. So you want to simplify globally the program that you have that has both of them together.
Or tensor networks, maybe.
Exactly. Yeah, whenever you have, especially in the form of graph, whenever you have a graph, it looks more and more similar to relations. So let's see one particular opportunity that we can see here. So this is a relational algebra, an extension of linear algebra expression, where it joins three relations, and on the join of these relations, it computes a group by count. So these are two join operations, and there is a group by count operator. So we can have a better version of this program by instead of first joining these relations and then doing group by aggregate, we can basically compute some partial aggregations in order to reduce the size of the intermediate results that we have. So basically, what this program is doing is that first it joins R1 and R2, and it computes a partial aggregate, and then it joins that partial aggregate with the other relation, and it again computes the further aggregations. So this is going to be significantly faster. So let's see from the linear algebra world, do we have a similar thing? That's basically whenever you're multiplying three matrices. So rather than having like a 5-level nested loop to do the multiplication of the three matrices together, we can basically first multiply two of the matrices and then multiply the result matrix with the other one. So on the database world, this is known as the pushing aggregate past join optimization. And on the linear algebra world, this is basically the matrix chain ordering. And one other interesting thing is that the choice of whether we should first do the multiplication of the first two matrices, then followed by the third matrix or not. This is also something that, for example, we use dynamic programming in linear algebra. And coincidentally, in the database world also, they are using dynamic programming in the query optimizer to decide about which join to perform first. So what I'm going to show you is a new intermediate language, which we call it STQL, that marries these two communities and can express both workloads in the same framework. So STQL stands for Semi-Ring Dictionary Query Language. So there is the dictionary term there. So let's decipher each of these words. First, what is a semi-ring? A semi-ring is basically the generalization of the idea of addition and multiplication. So we have a set of elements, R, and two binary operators, addition and multiplication, with two particular elements from that set, which we call 0 and 1, where we have a bunch of nice algebraic identities over them. So all of them are very intuitive. So for example, whenever we add an element with 0, it's going to be that element. Or whenever we multiply an element with 1, it's going to be again that element. Or if we multiply an element by 0, it's going to be 0. One interesting law is the distributivity law that connects the multiplication and addition together. So what are examples of summering? A very intuitive example is the set of real numbers and natural numbers, where basically addition and multiplication as well as 0 and 1 are the corresponding operations and identity elements. Another interesting one is the Boolean summering, where we have a set of false and true, and false is the identity element of disjunction, and true is the identity element of conjunction. And we have even more interesting summerings. So for example, we have the so-called tropical summering, which at the beginning it looks very counterintuitive. Instead of multiplication, we have the addition operator, and instead of the addition, we have min or max operator. And the identity element of the min and max operator becomes either plus infinity or minus infinity. Yeah? So believe me, whenever you do the calculation on your on paper, you will realize that actually the distributivity law applies also to minimum and plus. So we have deciphered what summering meant. The next keyword was a dictionary. What is a dictionary? So the dictionary, we know what it is. So it's a collection of key value pairs. And what is a summering dictionary? It's basically one collection to rule them all the other collections that in data processing is very important. So we are using this slogan, so we have to connect it to rings. So it's basically a dictionary from keys to values, where the values are forming, not quite a ring, a semi-ring. So what can we represent with that? We can use it to represent relations in databases. So in relations in databases, in the undergraduate course for database design, basically you would see with the set algebra, whenever the relations are each relation is a set of elements, so there is no duplicate. So you can represent a set of elements of type T as a dictionary from T to a Boolean value, where the Boolean value specifies whether that element is in the set or not. Or in practical databases, actually, you can have a bag of elements, meaning that an element can be inside a relation more than once. So we could have duplicates. To represent a multi-set or a bag, we can basically present it again as a dictionary from that element to its multiplicity. How many times do we see that in that collection? And also, we can represent a vector with a dictionary. A vector is going to be basically a dictionary from the index to the value that is located in that index. And a matrix is a dictionary from the pair of indices, the row index and column index, to that element. Let me show you visually how we can represent them. So basically a database relation. So here in this case, you can see a relation with two attributes, A and B. And as I said, we can have duplicate elements. So here, if we want to represent it as a dictionary, we are going to map, for example, A1 and B1, because we see them twice, we can map them into 2. And similarly for A2, B1, for A2, B2, we have only one occurrence of it, so we map it to 1. It's basically a dictionary from the tuple to the multiplicity. So how about a matrix? As I said, we are going to have a dictionary from the index to the value. So in this case, we only need to represent the non-zero elements, because the 0 elements are basically the 0 of that associated semi-ring. So we don't need to explicitly represent them. So basically, we can represent it with this dictionary of 3 elements, which are basically corresponding to M1, M2, and M3. So we have talked about semirings, about semiring dictionaries. We have to talk about now the query language part. And I don't want to show like the evaluation semantic of the language that we have or the grammar of it. I'm going to show you through an example what is the insight behind our language. So here on the left side, you can see an expression in the query language that we have and the corresponding C++ code for it. So here, for example, we have a summation operator. What does the summation operator do? It's a loop. So we are looping over a dictionary, and a dictionary is a key value pair. So we are iterating over the elements of R, name them as key and value, and then in the body of the summation, we are going to say what are we adding over inside the loop. And here you can see the corresponding C++ code. So we are iterating over the elements of R, and then we are adding them together. So here in the body, we are applying F over key and value. And in the body of the loop, we can go beyond scalar values. So we can construct other types of semirings. One of those semirings is actually the semiring dictionary itself. So here, in the body of the loop, we are basically creating a dictionary. So we are adding the values of these dictionaries together. And what does adding the values of two dictionaries mean? It means that whenever the keys are the same, we are going to add their associated values together. And perhaps this C++ code shows the intuition behind it very well. So let me show you a couple of examples. So here we have basically an SQL query that computes the number of elements in a relation. And here the relation can have duplicate elements. So what we are doing is that we iterate over the key value pairs. So as we can have duplicates, now we have to add their multiplicities together. And that's what's happening here. So we can also go beyond just the count aggregate. We can do summation of elements. So what we do is that inside the loop, we are summing up the values of this attribute, which are actually inside the key. However, again, we can have duplicate elements. So we have to multiply it by its multiplicity. And we can do also, of course, group by aggregates. So here, for example, we are computing the summation of A, but we are partitioning them based on the value of B. So the result of this one now is going to be a dictionary from the values of B to the associated summation of attribute A. And we have the conversion of all relational algebra to the language. I don't expect you to understand it. Just believe me, we have done some work. So similarly, on the linear algebra world, we can translate them into SQL. So whenever we are adding two vectors, it's basically like adding the associated dictionaries. No magic really here. How about the Hadamard product or element-wise product of them? So we iterate over one of the vectors, and we construct a singleton dictionary where the key is actually the index of that vector. For the value, we take the value of this vector, and then we look up the associated value inside the other vector. If that one is 0, then it's going to basically make it 0, so we don't need to actually represent it. But if it is non-zero, then we are going to basically construct that particular element. And to make it simpler, we can also compute the dot product of two vectors.
Do you allow a question in between?
Yeah, I'm fine.
I was just saying, you just said we don't have to put it in there if the value is 0.
Yeah.
On? No.
Yeah.
We don't have to put it in there. Are we allowed to put it in there? Do you guarantee zeros to be absent? How do you deal with that?
Yes. So in the runtime system, we actually normalize it. So if we see that it's 0, we don't represent it there.
Thank you.
Yes. And it's a very spot-on question, because if you want to use it for dense linear algebra, it can become problematic a bit from the semantic point of view. Yeah. So again, we did a similar thing for various types of operations in linear algebra. Again, believe me, a lot of things work except the inverse. We don't like inverse. And so in the array community, especially on the functional high performance community dealing with arrays, there is this notion of pool arrays. And here briefly I'm showing you how this language is connected to the notion of pool arrays. So what is a pool array? So it has an operator like a build where you specify the size of the array and a function together with it. And the function specifies at index I how should I construct the element associated with that index. And this gets translated into the following expression in SQL. So we iterate over a range from 0 to n, and then we construct singleton dictionaries mapping I to f of I. And that basically constructs this dictionary, which is actually the same thing as the pool array would construct. So we've talked about the language, the underlying constructs behind it. So, OK, we have a language. So what? We could express all these kind of things. We started all the motivation based on optimizing it. Let's see what kind of optimizations now we can do. And among all optimizations, we care more about the loop optimizations, because in most cases, basically, the loop optimizations are the ones that can give you asymptotic improvements. So we have a bunch of loop optimizations that are supported inside the language. 2 types of loop fusion, loop invariant code motion, and 2 other loop optimizations that you usually don't see that in that many systems. I'm going to, through an example, give you a bit of insight behind what we do with this loop memoization. So let's start with an example. We have a nested loop in order to iterate over 2 relations. And if we have if the join key of these 2 relations is the same, we join them together. That's basically a join in a database system. So an equality join in a database system. This is a naive way of representing it. However, if relation R has size n and relation S has size m, this is going to be O of m times n. So in databases, we know that they do something fancier. They do something of O of m plus n. I'm going to show you that with optimizations, we can turn this program into a program that is going to be linear cost. So let's see for opportunities. Here, we cannot really do any kind of loop invariant code motion, but there is one particular opportunity here. If we look at this snippet of the code, we can see that we can use an idea similar to the idea of memoizing a function. Or basically, it's known also as function outlining. Rather than doing inlining, we do outlining. So what we do is that we take this part of the code and we translate it into a dictionary instead. So yeah, we didn't really improve the performance here. But if we look at this program now there is an opportunity here. So this snippet of the code is now invariant with respect to the outer loop. So we don't have anything here that is dependent on these 2 variables. I can basically hoist it outside. And voila, what we have is basically what is known as the hash join operator in a database system. So we iterate over one of the relations. We construct a hash table based on it. And then we iterate over the other relation, and we look up on the hash table that we have created for possible joins. And this is going to be linear cost in many cases. There could be corner cases where it's still m by n. Yes?
I'm wondering about whether in general, like, how do you pick up on this specific construction? Like, is it that there's an equality to the sort of key? Is that what makes you pick up on constructing this temporary dictionary, or something else?
Yeah, it's because actually in the if condition we have an equality. If we had an inequality, then this was no longer possible.
That makes
So
sense.
it's based on the insight that whenever you have an equality, and when it's similar to looking up in a dictionary, because in a dictionary also we are looking for equalities.
That makes a lot of sense. Thank you.
Yeah. Yeah, but implementing this optimization is very hard. So this is not something that you would do with a rule-based optimizer, to be honest with you. You have to use more advanced techniques, which there is a workshop there for that. So I've shown you an example of the optimization. So one cool thing here with this language is that we unify the optimizations that were independently developed across the two communities. So in the database world, there is this notion of pipelined query engines, which at the end of the day, what they are doing is similar to what push and pull arrays, or in the functional programming community, what the deforestation is doing. The insight is that whenever you have a bunch of intermediate collections that are being consumed immediately after that, we can just avoid constructing that intermediate collection, or an intermediate array that gets consumed immediately. So this is the vertical loop fusion. Horizontal loop fusion is whenever you're iterating over the same collection several times concurrently. Then you can basically just have one iteration over the collection and do all the tasks that you're doing concurrently. So in the database world, this is known as a multi-aggregator operator. In the linear algebra world, this is basically called horizontal fusion. And what we did with the loop factorization and memoization, so these are very basic optimizations that we are doing. Whenever you combine them together, it will boil down to some of the advanced operators that you see in databases, which is, for example, group join or the hash join. And in the linear algebra world, this is basically the matrix chain ordering. So the next question is that, okay, is only optimization at the level of programs the only thing that we can do? And the way that I made it, it means that the answer is no, we can do more than that. So we can also represent different types of data layouts. So in the relation world, there is this notion of row layout and columnar layout. And in the dense tensor world, there is this row major and column major. Also in the relational world, there is this more advanced notion of factorized relations or factorized databases. And in the tensor world, basically, especially on the sparse tensor world, there is this notion of more compressed representation of tensors. So we can basically represent all of them with dictionaries or with composition of dictionaries, nested dictionaries. So what we did then was that we have several prototypes of this language. So we have an implementation of it embedded inside Python. We have also an implementation of it inside Scala. There is also an implementation of it inside Julia. And we have a bunch of papers published around that. And one of them is still under review. So what about the results? So we have good results, believe me. I won't go through the detail of the results. So we have 4 sections of the result, actually 3 sections. So one is on pure database workload, one is on pure linear algebra workload, and one is on hybrid workloads. And the takeaway from here is that the SQL system is competitive, or in some cases even better, than the systems that are specialized for that particular workload. So, for example, on the database side, we are comparing against two state-of-the-art in-memory databases. And we are competitive with them. So you could not use those systems to do linear algebra at all. They would be horrible to run linear algebra workloads. So for linear algebra, we are comparing ourselves to SciPy, for example, or NumPy. And we are competitive with them. For the hybrid workloads, there were some systems that could not support databases in general, could support only a fraction of hybrid workloads. Again, comparing with those systems, we were, in many cases, even better than them. So with that, yes?
Yeah, this is good, yeah. Hi, I was wondering whether there is a phase ordering problem when applying these rules, and did you do that manually or is it automated?
Yeah, so to have an apple-to-apple comparison here, so for example, in databases, there is this query optimizer that does the join ordering and this kind of things. And after that, it produces a query plan. So we started from the query plan that those databases had. So these optimizations that we have seen, they would make more sense in the context of the hybrid workloads, where there is no system to do the optimization properly. And there, yes, there was a very bad phase ordering problem. And so we came up with a phase, but the phase, I wouldn't argue that it's going to work always perfectly. In the second part, I'm going to show you one solution to solve the phase ordering problem. Any other questions? So,
have you considered including another array language into the benchmark, like APL? For context, I'm an APL developer.
Yes. So it would make sense only for the linear algebra to compare against them. And so the linear algebra, so here I'm basically showing using a sparse tensor workload. And APL-based languages do not work that well in the context of sparse tensors.
I think in the J language, which is from APL, they have an implementation.
Which language?
The J programming language.
Okay.
They have an implementation of efficient sparse arrays.
Okay, that would be interesting actually to compare against. So when I was looking at it, so I was looking at FootHark, for example, and it didn't have any good sparse support like that. I know that they are working on it now.
Yeah, thanks.
Yeah, thank you. So I'm done with the most, the deepest part of the technical discussion. Now I'm going to be I've become more and more shallow. And the next topic is actually the sparse tensor algebra. So we have considered these hybrid workloads. Now let's focus on tensor algebra, but a tensor algebra that is not in the realm of the array processing that much. So what do I mean by that? So we are all familiar with tensors. So in many applications, we have tensors. And recently, more and more, we are observing tensors which are basically many of the elements of which are zeros, rather than being basically many of the elements being non-zeros. And so here is where many of the techniques that people have developed in high-performance community fall short. So for example, there has been a lot of research on polyhedral compilation and this kind of stuff. They no longer apply in this domain. So the question is that, okay, what should we do? There is one slogan which every computer scientist knows, which is everything that you can see has been done in databases before. And this is basically, if you show this problem to a database person, they say, oh yeah, we have solved it. And yeah, they're not wrong. Basically, you can represent a sparse matrix as a relation. So let's consider this matrix, which is sparse. You can see many of the elements are 0. I can basically represent it as a relation with 3 attributes. The first attribute being the row index, the second attribute being the column index, and the third attribute, the value. And I can avoid representing the 0 elements. Yeah? So here, this element, which is in row 1, and column 1 associated with 3, you can see that it corresponds to this row. And for example, whenever I have this expression which corresponds to matrix multiplication, now I can represent it as an SQL query. What is the associated SQL query? So it's basically a group by aggregate. It groups by the row of the first matrix, the column of the second matrix, and I'm doing a join between the column of the first matrix and the row of the second matrix, and then I'm summing up their associated values. Yeah? So let's see how they perform. Not that good. Here, lower is better. You can see that DuckDB, which is one of the state-of-the-art in-memory databases, they're going to be around an order of magnitude slower than a system like Taco, which is the state-of-the-art for sparse tensor algebra. What is the reason behind it? So the main reason is that some of these sparse tensor tools are using data layouts that is basically compressing the representation of the sparse tensor. So here I'm showing an example from the Taco paper. So here, again, I'm using the same example matrix. So in relational databases, most of them, they are using a representation like this. It's basically a columnar layout representation of it. So they have basically one array representing each of the columns of the relation that we had seen. So if we carefully look at, for example, the array corresponding to the row, we see that there is a lot of repetition. We have 0, 0, 1, 1, 3, 3, 3. So the insight behind this compressed representation is that have some sort of encoding in order to get rid of this repetition that is happening here. So that basically boils down to a representation like this one. That makes it very complicated now, because now we are going to have arrays of different size, and size of some of these arrays is something that we have to determine in the runtime. Or more and more levels of indirection that we don't like. So what we did was that we prepared a framework which uses the language that I have shown you, STQL, a subset of it which we call STQLite, in order to represent both the storage layout as well as the computation. And then we magically optimize them together to produce efficient code. So let me show you a bit of these components through an example. So here we can represent the tensor computation and the storage format in terms of this language. So let's again see, this is basically the matrix multiplication, which is actually our tensor computation. We can represent it based on nested summation. We had seen it before. So how about the storage specification? How we can represent this one as an expression in terms of STQL? So here the insight is that we represent how we decompress the storage layout. So we said that one of the insights behind this sparse tensor framework was that they compress it. So we represent a program that would decompress it into its original form. So that's going to be basically this expression that whenever we apply it into these three arrays, it's going to construct this matrix. OK? Is the problem solved? So we basically we are doing matrix multiplication of two sparse tensors. We take their compressed format, we decompress it, and then we do the computation over the decompressed stuff. It looks OK, except that not. In terms of correctness, it's correct, but it's going to be very inefficient because we had the data in the compressed format, we decompressed it, and now we are doing the computation over it. OK? How should we fix it? Fusion. Let's do the fusion here and get rid of these intermediate collections that we have constructed. And as you have noted, Now we have the phase ordering problem. When to apply these fusion rules that we had seen. Yeah? As computer scientists, we are lazy. We don't want to design, engineer these rewrite rules. We want some magical tool that does it for us. So ideally, what I want is that I want to specify a bunch of equivalence rewrite rules, which we have 44 of them. And for example, we have one particular rule to do the fusion. And we have another rule which basically does the factorization. So this one is very interesting because you can see that it not only does the loop invariant code motion, but it also actually puts the operator outside. So here, if we had n multiplications, we are going to have just one multiplication here. So we have 44 of these kind of rewrite rules. Then we are using the equality saturation technique. So what does the equality saturation do? You give it a database of rewrite rules. You give it a cost model. It searches. It tries to apply all these rewrite rules. It creates a search space, and then it extracts the program with the minimal cost with respect to the cost model that you gave it. And the search space it can become very big. Because of that, it basically it has a data structure called an E-graph to basically have a more concise representation of that. And on that note, basically we have, together with Mikhail, we have actually a paper in PLDI where actually we improve even the technique, the equality saturation for examples where we have variable bindings, which actually appears a lot in the language that you can see here. The talk is on Wednesday, right before lunch. So after that, when we apply this, what we have? Problem solved. Lower is better, and the most left one is us. We are not only better than the database systems, we are also better than the state-of-the-art tools. Why is it the case? It's because of this systematic way of applying rewrite rules. Now we can detect some further optimizations that was missed by some of these state-of-the-art tools. We not only do the compressed storage, we also do algebraic rewrite rules that were missing. So on the same line, to apply for sparse tensor algebra, my student Mason, who is sitting there, we have actually applied it in another context as well, which is for quantum simulation. So in quantum simulation, basically what you're doing is that you're computing a bunch of matrix or matrix vector multiplications. However, if you look at the matrices that exist in quantum simulation, you see that they are sparse, or there is some structure there. And we basically have a bunch of sparse matrix multiplications. So we have used the same language in order to capture this sparsity. And here are some results that we have. So in addition to the C++ code generator that you have seen, we have also implemented the GPU backend. And you can see that, so the rightmost one here is our tool, and here higher is better. So, and Quest is basically one tool that is highly tuned by some amazing material scientists who knew a lot about high-performance computing. So it was basically 2 or 3 work during their PhD that basically Mason managed to do in less than a year by using this technique. And the reason for that was because, again, we could leverage some of these optimizations exhaustively that they had to basically write down each of them in low-level C code. And this has appeared in CGO this year. Okay? So I'm going to quickly go over the automatic differentiation one, just to give you a very high-level insight behind it. So automatic differentiation is something that is heavily used for machine learning, training in machine learning, where you have to basically write a compiler that automatically computes the differentiation or the gradient of an objective function. And what we realized was that in the community, there was a lot of work on automatic differentiation for dense tensors. But whenever you had some sparse tensor computation and you wanted to do differentiation over them, you would usually get some cryptic errors that you don't have any idea why TensorFlow or PyTorch do not work on them. And then whenever you dig in and go to the GitHub page and go to the issues, you realize that, OK, they don't support automatic differentiation for sparse tensors. And so what we did was that we used the same framework again, and we captured the automatic differentiation inside our intermediate language. And then because of the separation of the concern that we had, we could basically represent the storage layout also as an expression inside this language. And then we applied the same technique, and we managed to basically support be the first framework that supports automatic differentiation on top of sparse tensors. And we could basically scale it to much, much larger sizes. So I'm going to skip over the last topic because we don't have time. So I'm going to briefly say what that is about, which is basically about something in the middle of dense tensors and sparse tensors. So with dense tensors, the cool thing is that we can do vectorization, parallelization, and cache locality. With the sparse tensors, we don't have them, but instead we can have better storage layout, have better computational complexity, and scale it to much, much larger sizes. Can we combine the benefits of both these two words? And the answer that we found was that for a particular type of sparse tensors, which we call it structured tensors, where we can basically capture the non-zero elements as a shape, we can do a much better job on combining the benefits of both. And this is what we call the structured tensor algebra. So I'm not going to show the details of that, but yeah, we have work in UPSLA 23 and UPSLA this year around this topic. So just to summarize, so I was advocating for dictionary processing. So we had seen for hybrid workloads, we could represent relations and tensors with dictionaries. In particular, for sparse tensors, we have seen that we could use dictionaries to represent at the logical level what the tensor computation looks like, and then how we can represent also the storage layout as a kind of conversion between dictionaries and arrays. And also the last topic that I didn't have time to go over was structured tensors, where we can capture the structure information. For example, what is the sparsity pattern, or whether there is redundancy there as in terms of dictionaries. To conclude, so data science is very important, but it's a double-edged sword. And we need to basically radically rethink about the data science pipelines. So here in this work, I mainly focused on one of the intermediate languages that we have created in my lab, which is called STQL. We have a bunch of other intermediate languages for other types of workloads, where I gave pointers to them. And the nice thing here is that we can now leverage the structure inside the data, inside the language, and teach the compiler how to leverage that structure. And as a result, we can basically optimize across the data science pipeline. With that, thank you so much for your attention.
Thank you very much for the inspiring talk. Maybe we have one quick questions, if there is any left. Go ahead.
For storage optimization, have you considered inverted tables?
Can you elaborate a bit more?
So inverted tables is basically a table with a vector with columns stored as individual nested vectors. And the benefit of that is that if your column has a certain data type, having it as a single vector would just be just a simple array, which is a nicer in terms of storage.
Yeah, so that reminds me of blocked storage formats that
Yeah.
Sparse Tensor framework has. Yeah, so this framework actually supports that. So it's quite expressive in that sense. So it can basically support many of those structures. One caveat here is that one nice thing with this kind of block formats is leveraging vectorization opportunities and or parallelization opportunities. So on that side, we are still far behind what we can basically fully leverage from vectorization. On that line, basically the last work that I didn't have time to go over actually deals with how to leverage the vectorization and cache locality better.
Okay, thanks.
Yeah.
I'm afraid we have to take this into the break, and we shall reconvene in half an hour, 10:30. Thank you very much, Amir.
Thank you.